Okay,
Okay.
the last thing that we're gonna show you guys. So this is a bit of a bonus video. So you're actually gonna see me live code for a short while. Um, so this okay. So I guess I'll leave it in comment first. So if you guys remember, one of the previous statements that we proved something like for all n in what z. Oh, it's got autofill. For all a, b, and z, something along those lines, right? Then we said that if n equals to a, b, right, then a at most square root n or b at most square root n, right?
Just a random like it's
Mm-hmm, mm-hmm,
aside, but
mm-hmm.
then how particular are you with the brackets and the like, operator precedence and stuff? The
I
like
told the students that
how
we'll if we give them a formula, we'll try to be as explicit as possible. And if it's unclear, they should just clarify with us.
then what if the students have to write the the connectives and propositions? Like for example, you see your
Parenthesize
line
everything.
5. Yeah. Like
Oh, I
should
see,
you
I
put a
see.
bracket around the or?
Yeah,
That
yeah,
is my
you should. Yeah. Okay. So
okay.
so to make things a little bit easier, I'm just gonna scope it a little bit better. I'm just gonna say like for all n in n, for all n in n, right? Okay, so the why is this statement useful? So let's just say, right, hypothetically, your boss comes to you and asks you to write a is prime function, right? Well, I don't think he'll do that, but I don't know. Some of you
You
might
just
be
call
working in places that
library in this day and
call
age.
library. But is there a library function for Python that does primarily testing?
I don't know. There's only one way to find out.
The only one way to find out, Google it, right?
Yeah.
Okay.
No
I
worries,
guess
you
you
can
can
keep writing.
Google.
I'll just
I'll
yeah.
keep writing, right? Okay. So here's
Yeah.
a very simple way to test whether a number is prime. So remember, a number is prime if and only if. Oh, I actually whipped out the if and only if. Oh crap! It actually does show up. Like in anyway, a number is prime if and only if um
Greater
how should I
than
say this?
2.
I mean, yeah, sure. Okay, so if n is greater than or equals to two, greater than or equals to two, and right, the only two divisors are one and n. There's a way of writing this mathematically, by the way. The way you would write it mathematically is you would say if d divides divides n, then d equals to one or d equals to n. This is how you would write it mathematically, right? This means that n is prime. Right? So I actually should write a for all d in n. If okay, let me spread this out a bit. But this is how you write this mathematically. Okay. But anyway, not the point right now. So let's try doing that, right? Let's literally try implementing this statement. Okay. So you would probably do something like for all d in oh wait, sorry. So if n less than or equals to one, we return false, not a prime. If not, we do for d in range 2 to d, because range, by the way, is left exclusive. Left inclusive, right exclusive. So this will iterate up to value d. If you don't believe me, let's test it out, right? So print d, right? So let's see what this does. So we're gonna have to get some value out. So I guess I'll just call it is prime right now, and let's test it for value 10. Let's see what it runs. Let's see what it prints, right? So it should print unbound local variable.
And
Sorry,
two
and
domain.
yeah. Okay, there we go. Right, so see, it starts from 2 and it iterates until 9, then it stops, right? Okay, so we know it's only testing those values. So we're going to say this, if n mod d is 0, in other words, there's no remainder, right? In other words, the remainder is 0, then we know for a fact d cleanly divides n, right? So then we're gonna return false. Okay, otherwise at the end of it, we didn't find a divisor, we're gonna return true. So I'm just gonna print out the result. So I guess I'll write it this way. If is prime, we'll print out prime. We can use f string, right? So I guess I'll put n here. N equals to 10. We'll test number n and use an f string and we'll say n is prime, right? Otherwise, we will say n is not prime. Okay, so let's just quickly test this, see if it works. This is 10 is not prime. You want to give me another number?
9. Prime number
Okay.
7.
Oh no, I said another number, but prime number works
Oh,
too.
okay.
So now
I
you
need to
should, yeah, you
test
should still have it
both
as prime.
cases. Yeah, okay.
Right, so yeah, test a few lah. Let's just okay,
Yeah,
16 is a
yeah.
bit too not interesting. Let's try, I don't know,
What is an
some
interesting
seemingly
number?
prime number, right? Like 30 what, 41? Let's try 41, right? 41 is prime apparently. Is it? I don't actually really know. But I guess if the program says so, it's probably correct, right?
Yeah, I trust the program too.
Trust the program, right? Okay.
Yeah.
So here's one thing that like I'm gonna do. I'm gonna actually also have a iteration counter. So I guess I should put that. Where should I put that? I guess I'll put it, I don't know, like I'll put it here. I'll say like, okay, printf, print iterated, made d
You
iterations.
should put it outside of the if statement bar.
No, because if you do it here, if you do it outside, you know die, you must have made d minus one iterations, right?
Right.
You know what I mean?
Okay.
Whereas on the inside, the
D
moment you
minus
early terminate, you're returning, so you know you made d iterations, right? So let's try, right? So if it's prime, I made 39 iterations.
Oof, okay.
I think so. It's around d iterations lah. D minus one, d minus two, close one I, okay. But if let's say I have a number like let's say 16, or okay, let's try 25, right? So it only makes 5 iterations. Okay. So I claim the following. Okay. If a number is not prime, it only makes at most square root n iterations. And also, if a number is prime, it makes d minus 1 iterations. Right? So for example, 25, right? I only make at most 5 iterations. You are not, it's not possible for you to find for me a number where it is not prime and you will make more than square root of n iterations. So I'll give you another example, maybe like 49. This is not prime. I only make 7 iterations at most. But if you give me something that's prime, right? Like for example, I actually don't know what prime is anymore. I'm just gonna like mash a bunch of that's obviously not prime. Maybe this is prime. I don't know. Let's see,
No,
right?
it's
Yeah. I mean, okay. The odds of it being prime are very small,
Yeah.
actually, but it's 1 over log n actually. Like for anyway, right? But look, even with such a massive number that's not prime, right? You're only gonna make very few iterations. You're only gonna make very few iterations, actually. Okay, so you might spot the pattern here and say, oh, okay, if I never make more than square root n iterations, right, for a number that is not prime, how about we do the following, right? Actually, I don't know what's the correct, like, is it, let's see, import math. Let's try it, right? So instead of iterating from 2 to n, why not do this, right? So instead of iterating from 2 to n, hold on. The shortcut keys don't work the way I thought they worked. Why not iterate from 2 to math of square root n? Oh, I might need to plus 1 here, right? Something like that. So let's test this on 25. Oh, yeah, okay. Float cannot be interpreted as an integer, so I need to cast this back to an integer. So let's do that. Something like this, right? So you only make 5 iterations at most. Where, okay, just to be clear, right? I want to test this out. I want to see what happens here. Yeah, okay. So we need the extra iteration. We need the extra iteration.
Wait,
okay.
Do you add the plus 1 wrongly?
Should it be on the outside? Oh, it should be on the outside, right? Yeah.
Okay.
Good catch. Right? So what's going on here is that we're cutting our program short, by the way. We're cutting our program short by saying you're just going to try up to square root n iterations. And if by the square root nth mark, you don't see a divisor, right? It's definitely prime. You don't have to try the remaining value, the remaining divisors. Right? So again, something like 49, right? You're only gonna try 7 iterations, you're gonna realize it's not prime because you're gonna find it, right? But something that's obviously prime. What's obviously
41?
41?
Oh,
yeah.
Yeah.
Right? You only have to make 5 iterations now to argue that it is prime, right? Whereas the previous program had to run 40 iterations, right? So we only have to run 5 iterations now. We've sped our primality testing program up. Okay. Now this sounds like black magic, right? Because why do this, right? Why is this true, right? Like, why did we do this optimization? Why did we change from this for loop to this for loop, right? We changed it because we think this is true. We suspect this is true. When a number is not prime, it only makes at most square root n iterations. When a number is prime, it makes d minus 1 iterations. Okay, so why is that true? Well, think about what the original mathematical statement is saying, right? The original mathematical statement is saying that if you go through any natural number, if there is a way of factoring it, one of the factors must be at most square root n. So let's think about a prime. So a prime number can only be factored one of two ways. It can either be 1 times p, right? Or it can be p times 1. Okay, so my divisor test starts from 2 onwards, right? So my divisor will start from 2 onwards until well, in this case, until square root p, right? So question for you, among these values, right, will we ever find a divisor for p if p is prime?
No.
No, right? So we will always drop out of the for loop by the square root p mark, and we will return true it's prime. Okay, what if p is not prime? So let's use a value, I don't know, let's use a value m. So let's say m is not a prime number, right? So there can be multiple ways to factor m, by the way. It can be 1 times m, so on and so forth, right? We're gonna skip 1. We want to skip 1 as a divisor, but there's going to be some factoring. There's going to be some factoring where either a is less than or equal to square root n, or b is less than or equal to square root n. This has to happen. This has to happen. Okay, and also furthermore, it's going to be the case that like a is like, you know, whichever number it is, right? So I'm going to say right now, 1 is greater than a is greater than 1 and b is greater than 1, something along those lines.
And less than square root n, yeah.
And less than or equal to square root n, yes. Okay, so you can actually mathematically prove this actually, and what's going to happen is that what that means is that when you test the divisors from d all the way up until square root m, one of them has to be a divisor for m actually. Okay, because of that, what that means is that when a number is not prime, there must exist a value d that happens to be within this range that, you know, that can divide m, right? Or I guess in this case n or m, whatever you want to call it, right? So we can actually quit early and say it's not prime. And after that point, if you pass the square root m point and you couldn't find a divisor, you are now happy. You don't have to look at the rest anymore. Like 100% you're sure it's a prime number, right? So knowing the math like this helps you write optimizations in programs, which I don't know how surprising that. I don't know. Do you find this surprising? Like,
I guess.
You don't sound very surprised for someone who's saying that he's surprised, I guess.
I'm still trying to think about the first time that I figured this out, you know. I mean, at this point, it's not surprising, but...
yeah, because you've done this a long time ago, right?
Time travel back to the moment I first figured it out, yeah.
You first figured it out. Actually, I don't even know when I first figured this out. This was very long ago. This was like... It's probably been like 10 years ago for me now since I've actually figured this out.
I have no idea. If you Google like how to find prime numbers, you'll always find this square root n iteration.
Is it? Isn't it like the sieve also? But sieve is a bit different. But there's the sieving method.
Yeah.
Yeah. But the point I'm trying to get across, right, is that like these things aren't taught just because, you know, someone decided to pick a random topic and say we're gonna torture all the CS kids with this. Like it's not. I promise you, it's not, right? But I guess like no one has ever told you why we really use these things. I know of a lot of optimizations that work this way. They uses math like this, but they're too complicated to explain in a short video. The proofs are way too complicated, right? And we are not at the level where we can discuss those because there are bigger fish to fry right now, like getting your foundations up, right? But my point is that this is the best example I know to show you how you can actually write fast programs, right? And in computer science, I said this before, we're in the business of being fast and correct. That's what separates us from, you know, monkeys who write glue code. Like that's really what sets us apart. So, you know, this is the best motivation I can give at this level, at the introductory level. So yeah, anything else to add, Yongrong, before we end the video?
Nope. I'll see you all next week.
Always the same comment.